the following.
Merci. On enchaîne avec le prochain communicant ou bien communicante, c'est Madame Barbaris Marwa, Université Farhat Abbas. Université Farhat Abbas, qui va nous parler Behavioral Study of Composite, honeycomb sandwich structure, aluminium sandwich, aluminium à peu près 10 à 15 minutes. Ok.
Assalamu alaikum. Can you guys hear me?
Microphone.
Good afternoon, everyone. Thank you for coming here today. I'd like first to introduce myself. My name is Marwa Barbaris, a third-year PhD student at University of Farhat Abbas. As you can see on the screen, my object or my subject today is the behavioral study of composite honeycomb sandwich structures, AL9X. I'd like briefly to talk about sandwich structures and then give you an overview of the objective of my study. So, the field of sandwich composites, particularly honeycomb structures, has generated growing interest in recent decades due to their numerous industrial applications. Sandwich composites typically consist of two rigid outer layers called facings or skins and a lightweight strong core, often in the form of a honeycomb. This unique configuration gives sandwich composites exceptional mechanical properties such as lightness, high stiffness, and strength. The objective of this study is to simulate the behavior of honeycomb sandwich structures and the mechanical loading and three-point bending test. The use of numerical simulation allows for obtaining various local insights, particularly at the skin core interface of the honeycomb. For their applications, sandwich panels offer many functional advantages, such as a better mass to stiffness ratio, reduced maintenance, very improved mechanical properties, etc. Their applications is due or depending on requirements of industrial sectors as transportation, automotive, aerospace industry. So, for the honeycomb materials, I used as pores in sandwich structures to maintain the separation between the skins. The mechanical properties vary depending on the type of loading. They're recommended for their out-of-plane compressive strength and have been characterized under different types of loading. We can see some examples in the figure 1.3. So for the bending test, the material we're using today in this study is a sandwich material with the aluminum Nomex honeycomb core. It is supplied by Oro Composites and intended for the aerospace industry. The structure of this type of sandwich consists of two-dimensional Nomex cells placed in the plane of sandwich with an aluminum skins. Table 1 shows the specimen dimensions for the three-point bending test, while Table 2 and Table 3 shows the mechanical properties of both the skin and the Nomex core. Which leads me to talk about my next slide, or my next point, which is the experimental procedures. So the bending test is conducted in accordance with an ASTM C33962 standards and carry out in two different laboratories with the three different specimens. And we can see in the figure 2 the setup of the flexion machine with the configuration core of both longitudinal direction L and transverse direction W. So figure 3 shows the mode of failure of the honeycomb structures, and the next figure is a figure that explains the charge differences as function of the flash or the deflection. We can compare it to 3 different stages: an elastic stage with a peak, a maximum value, a bending resistance stage of the sheet with a rough drop of the value, the maximum value, then a sheet stacking stage that goes with a decreasing of the charge to a maximal deflection. To analyze the thermomechanical behavior of such material, we're working on a specimen of 200 mm of length, 10 mm of width, of thickness, and 40 mm of width. We can see on the figure 5 the low deflection curve for AL-Nomex sandwich panels as function of temperature. As we can see in this figure, not forgetting to mention in the direction L. So we can notice in this graph that the peak is much more higher when the temperature is of 20 in a room temperature, 25 degrees Celsius, than the peak in 150 degrees. While figure 6 shows a specimen during test and after test, or at the end of the test, figure 7 shows the low deflection curve of AL-Nomex sandwich panel in the direction L with a D or density of 144 kilogram per meter cube. We can see in this test that the behavior can be also broken into 3 stages. The first one is a linear behavior, and the second one is a non-linear behavior that can be explained with the buckling of the cells. The third stage is the stage where the decreasement of the charges occurred, and we can hear some cracking in the heart of the Nomex or of the sandwich. These 2 figures shows the different tests with the same previous conditions, but with a different sense, W transverse and A longitudinal, for different densities, for 144 and 80 kilogram per meters. For this test, we can see that both behaviors are slightly similar, but with different values of deflection of charge, and we can explain that by the difference of configuration and density. Before running our simulation, we developed a model in SolidWorks, as we can see it in figure 8a. Then we imported this model with a plugin file in Abacus, so we can manage to make the machine without forgetting that we give the program the law we are using, the modeling law, the geometrical model, and the condition boundaries or boundary conditions. In order to reduce the computational time, as we can see, this model is complicated and contains a lot of machine elements, so decided to make another simplified model instead, which contains the most important elements to make to run our simulation. So the figure 10 and figure 11 shows the results of the numerical simulation. As we can see here, the load or the stress, the maximum value, is located exactly under the contact area, the red zone. This area is the area experiencing the most stress values. Here we highlight the comparative study of morphological evolution during flexion test from a qualitative point of view. The finite element calculation determines the loading value. It is observed that this load reaches its maximum amplitude at a value of 6 kN. In order to compare the calculated and measured results, a significant discrepancy is noted between these values. This can be explained by the mesh density used in the loading area. We hope to make a very dense meshing or more number of elements under the loading area, but we couldn't use the calculation system in our university, so it's to improve. For the effect of temperature, here we can see that from the temperature changing from 25 degrees Celsius to 215 degrees Celsius, we can see that the charge loading of vomizes is decreasing from 302 megapascal to 295 megapascal. But for the friction influence, no huge results are taken as. In another word, for the friction, no change in the morphological way is noticed. So to sum up, in this study we conducted quasi-static 3-point bending test on an aluminum Nomex sandwich composite, varying the core density, temperature and orientation L and W. We also carry out modeling and numerical simulation using the finite element software Abacus. The comparison between the morphology of the sandwich panel during the simulation and during the experimental test shows a strong similarity. This indicates that the simulation results satisfactorily replicate the behavior of sandwich panel. The failure of Nomex LL sandwich, depending on the core density and for different temperatures, is characterized by crushing the cell walls in the honeycomb core in the sandwich, localized indentation of the upper skin at the loading point, and a plastic deformation of the skin. Using a finite element model simulations were carried out to study the behavior of the sandwich under different conditions. The results showed that the test parameters such as temperature have a significant impact of the bending performance, while the coefficient of friction does not have a notable influence. And thank you all for your attention.
Very good presentation.
Thank you.
I like it very much of the work.
Oh, thank you.
Any question? Then I have the thickness
The thickness.
of the face of the sandwich. What thickness? What thickness?
What's in it, like a material, or how much is it?
The honeycomb.
It's a
no.
very, very thick.
The face.
Yes.
Face, one face, or
The
the
second.
face, honeycomb.
And the heart, yes.
The face. What thickness? What?
It's an aluminum.
Yes, but how much millimeter?
It's a very, very thin. It's about 2 millimeters, 3 millimeters, I guess. I'm not sure about it.
Then, the same thickness that you use in aluminum in the experimental part, you use in the
Simulation.
in the finite element method.
Yes.
The same thickness,
Dimension.
the
Or
same
material.
the same thickness of the face you use 2 in the finite element method, yes?
Yes.
Okay. Then you use temperature in this model,
Yes, with an
Yeah.
MTS machine, experimental test.
and you use the finite element of solid world.
Of abacus, yes.
Ah,
SolidWorks is for the model, geometric model. The machine or element finite is used in abacus.
Very good, very good, very
Yes.
good. Okay, okay. The model in solid world and room.
Yes, it's
In
imported. When we make or when we develop a model in SolidWorks, we can import it to abacus.
Import abacus.
They work together in one conditions that we registered it with a step extension. With a step extension, yes. So the step extension is readable in the abacus. Yes.
Okay, I understand. The last question.
Yes,
In
please.
the experimental part,
Yes.
how you glue the honeycomb to the face?
How did I make the
You have the face in aluminium, one face. You have the honeycomb. How you bond it? One which other? How bond it?
So to be honest,
In order to do the sandwich composite,
yes.
you need to do the face first, the
Yes.
second face, okay, and you need the honeycomb. Are separate.
Yes, to make them
Honeycomb,
stuck.
face. How
Yes.
you bond it? How you glue it?
Yes.
One with the other.
First of all, those specimens were offered by an oral composite company to 1erjour in France. So those specimens were given to me, so I can use them already bonded together. But I can explain that how there is some adhesive films to put between the heart or the core and the two skins. It's in glue, industrial glue. Its name is M3. It's a very commercial glue that can maintain the adhesive between the faces and the core.
Okay, and then when fracture in the test in the flexion, you use 3-point flexion test. 3-point
Bending test. Flexion
bending test. Okay.
Yes.
In the moment of the fracture, where have the problem? The bonding, the honeycomb to the face.
Only when I worked with a temperature of 115, the glue had fission, and the laminate is occurred to the inferior skin. Yes.
Okay.
How to solve that? I don't know.
Okay.
Yes.
Very good. Only the word.
Good?
Only the part of simulation
Yes.
with temperature in abacus is very good, very important.
Thank you, sir. I appreciate it. Thank you.
Congratulations.
Thank you, sir.
Okay.
Done.
The last presentation is Mimouni Murat, University of Lord, Algeria. He's here. Okay. The title is Effect of the Monomer, Natural and Neodymium Doping on Structural Property of being 2212 superconductor. prodotti power prepared by photopolymerization method.